Hello, y'all. This is Darrell Berry Jr. back with some more linear algebra, picking up where we left off last time with the spectral theorem, which, as the book said, relates to spectra, which is a favorite of mine in astronomy. So we'll take a look at this and see what we get in the proof. So now we're at the proof of the spectral theorem. And look at so since we begin by proving that the eigenvalues of a symmetric matrix must be real. So this is going over what we did earlier, where we had a symmetric matrix here with the squares inside this is a symmetric matrix, AT equals A, and this is the determinant, at least the characteristic polynomial of that equation, which is basically I take the determinant of A minus lambda I, and that gives me my uh, characteristic equation. Basically, we simplify everything. We end up with a quadratic equation. And because the b part is squared, there's this part here. We have multiplying everything out. It simplifies so that everything is squared. Doesn't look like it up here, but everything is squared. So since everything is squared, nothing is negative. Even if we had a negative up in here somewhere, it'll cancel out in a nice way. Thus we have all the lambda eigenvalues to be real, right? So the proof begins with a trick to turn complex entities into real. So we already proven that the eigenvalues of a symmetric matrix are real from the squares. So now we have to turn complex numbers into real numbers. So I didn't actually go through the details of how they got lambda out of these variables here. But we do know that in general, a complex number is a plus bi. It's a general complex number. So we're saying that our eigenvalues are complex. We say lambda equals a plus bi. So basically every number is a complex number, just that b is usually 0. So that's all lambda. A complex number or potentially complex, because b could be 0. Eigenvalue, a potentially complex eigenvalue of a, and we're going to consider the real matrix S equals a minus lambda I a. So what he's doing, trying to break this down and think of it in the quantum mechanics format. As we talked about before, this book skips a lot of steps. As we go farther into the book, I like the book less and less. But I know from quantum mechanics that if you want to take the magnitude of a complex value, we have to take the uh, complex conjugate. We have the positive I times the negative I, and then the imaginary part cancels out. And we know that we get determinant of a minus lambda I equals 0 to get the characteristic equation or the characteristic polynomial. So if lambda is complex, then we take a minus lambda I, and to make it real, we say a minus lambda positive I times a minus lambda negative I. So the matrix they're saying is a minus a plus bi I times a minus b I. So we're going to multiply this out. So that equals a squared minus a minus b I minus a plus b I, and then minus or plus a plus b a minus b I squared. So that equals a squared minus a I a minus b I minus a minus b I plus a squared minus b I squared, both of these squared, I squared. So that equals a squared minus a I, so plus 2bi plus a squared plus b squared I squared. And let's see if I'm getting closer to what they had. Maybe I need to distribute this negative better. So this would actually be plus and plus. So let me back up. Need to do this ironically in most steps. A squared minus, so I'm going to factor out the negative a I. So that equals a minus bi plus a plus bi plus a squared minus b squared I squared I squared. I guess not more steps, but more accurate steps. Because when I factor out the negative a here, then this becomes a positive on that side. So then it becomes plus a plus bi, not minus. So that becomes a squared minus ai 2a, because the bi's cancel out. And then we have plus a squared I plus b squared I squared. Now, up in here somewhere, they make this, it looks like, okay. Now, why don't they get an I squared at the end? Let's see. So we have A, we have seems like I have a extra I squared. So somewhere up in here, they have a single I on the B squared and the squared on the A. So basically, if I had uh, A and AI minus minus. So maybe they added something up in there. So if I multiply this out, I will get A squared minus 2A AI plus A squared I squared. So I would have to subtract A squared I squared, and then I still have the A squared I, and then plus B squared I squared. So then I would have A minus AI squared. And then maybe I could do something with the other end there. Minus A squared I squared. Yeah, I think they skipped too many steps. I'm not seeing what they did to simplify this. Let's start over one more time. But that's what I mean about this book. So the proof is based upon this simplification, but they kind of like just have the whole thing in like 3 steps right here. So yeah, the farther I get along in this book, the more I hate this book. I think the early parts were written okay, but as we go along, they seem to just not like, maybe they got tired of writing and just wanted to hurry up and finish it or something. They just don't put enough steps. Maybe they did need to save pages or something. I don't know. That's equals A minus A minus B I A minus A plus I. So that equals A squared minus A plus I minus A minus I plus A minus A plus I squared. That equals A squared minus A minus I can just distribute that as well. I minus I minus A I plus I plus A squared. So then it's going to be plus ABI minus ABI minus BI. Oh, I'm writing my I as a sub. B squared and I squared is -1, so that's plus I. And I could just distribute the I squared now. So that's A squared, I squared plus B squared, I squared. Right? So this AB, I minus AB, I cancels. So that seems to be the cancellation that made the difference. So if A squared minus AI, so minus 2 AAI plus A squared plus B squared. And let me just write it out. A squared I squared plus B squared I squared. All right. So now we have what we need to put this thing into squares. I still have an I squared. How are they not having an I squared at the end of this? Right. So maybe there's a typo in the book. I'll do even more. So S equals A minus A plus BI. A minus A minus BI. So that equals A minus A AI plus BI A minus AI minus b I I. Perhaps it's better to do it in threes, right? So I distributed the I into everything, the capital I, and this should still give us the same answer. So now we have a squared minus ai minus a b I b I minus a plus a squared I squared plus a I squared b I plus b a minus b I a I squared minus b squared I squared is plus I squared. So I still get the I squared. Let's see if they just made a typo on this thing, and I'll stop doing this over again. Maybe I could put it into a calculator or something. So we have minus capital A B I plus, so that still cancels. We have plus AI squared BII and minus AI squared BII. That cancels. Um, so we have A squared minus AI minus AAI, so minus 2AAI plus A squared I squared plus B squared I squared. Yeah, so I think they just made a typo. I think they made a typo and they should have had an I squared here. So right here, it seems like it's necessary to have an I squared right here and right here. So, but I shall just in case, actually, but I'm still not seeing how you'll get out with a BI with no I on it, since that whole thing is multiplied by I. And at the end, it will be B squared positive with the I and then I squared. Oh, I see. No. I was about to say, so in other words, I think what they're doing is, like if I have an identity matrix that equals 1 plus 0, 0 plus 0, and 0 plus 0, 0 plus 1. Okay, that's what they're doing. So they're simply multiplying the identity matrices together, and you can still end up with an identity matrix, which I should know. So I squared equals that equals I. So just the identity matrix squared is I, but they just choose not to square it. They choose not to make it one here to complete the square. So I guess technically we could always input an infinite number of identity matrices times each other. Okay, so it's not a typo, it's just a simplification that maybe was clarified earlier in the text or something. I don't know. Minus AI squared plus B squared Okay, so now we have the exact thing that they have in the book just by remembering or recognizing or knowing that the identity matrix squared is itself, but we're just not doing it here so we can complete the square. So apparently we could just throw in identity matrices, whatever we need to complete the square. So we'll keep that in mind for the future. This is just the usual multiply by conjugate trick from high school algebra, since determinant and the multiply by conjugate, by the way, is the fact that we're, like I mentioned earlier, the complex conjugate. The complex conjugate is when I take the positive and negative complex number here, the positive and negative of the complex part. Since det A equals 0, so since det A minus lambda I equals 0, in order for the matrix to be singular so we can get a proper eigenvalue and eigenvector, it follows that S equals 0. Thus S is singular. So there's a non-zero vector X. That is not 0. That's NRN, such that Sx equals 0. So since Sx equals 0, then Sx dot x equals 0. I mean, it seems like everything is 0. S is equal to 0. Sx is equal to 0. Suppose we could throw in as many x's as we want to still make it 0. So 0 equals Sx dot x equals interesting. So we're going to insert this S so that equals all right. So we're using a property of dot products where if one of the things are summed, you can go x minus ai squared dot x plus b squared I x dot x. So this is what they did for the next step. All right. and using symmetry. I believe here there's some skip steps again. So maybe I'll come back here another time and we'll finish from this. But we did figure out S, what S is here as a part of this proof. So run about 30 minutes. So come back for the next one and we'll continue right here with this proof. Like, subscribe if you haven't. Help me get to 1,000 subscribers. I'll see y'all next time.